Good morning, everybody. Welcome back to our study of stellar pulsations. In yesterday's lecture, we have considered small perturbations around a hydrostatic stellar model, and we have derived the equations governing or describing small spherically symmetric perturbations around the background model, means radial perturbations with spherical symmetry around the hydrostatic stellar model, or in other words, around the background model. We were left with linear equations. We have assumed that the perturbations are small, and as a result, we have obtained linear equations which were partial differential equations, both in the spatial variable taken to be the mass and the time as the second variable. Now, as these equations are linear and the coefficients did only depend on the background model, we were able to separate the time dependence in an exponential form, which left us then with an ordinary differential system of fourth order, but containing the time dependence as a free parameter, which we denoted by eigenfrequency or eigenvalue. So we are left with, after some manipulations which were done in order to enable a convenient numerical treatment of this system of equation, we were left with this fourth order ordinary differential system containing the eigenfrequency, which denotes the time dependence of our perturbations, and coefficients, which were dependent only on the spatial variable and contain, so to say, the information on our background model or on our hydrostatic model. So these coefficients, well, coefficients C1 to C3 and C4, together with the derivatives of the opacity and the equation of state. So this information about the background model plus the eigenfrequency appearing here, these are the parameters of our differential system. A differential system needs for its complete solution boundary conditions or initial conditions, and we have asked ourselves what is a physically meaningful boundary condition, and we found out that we have actually two conditions which we have to take because the coefficients become singular at the center, and so for as a regularity conditions we have to adopt these two boundary conditions at the inner boundary, and we are not allowed to take any other boundary condition, because otherwise we would capture some diverging solution or contributions from diverging solutions which we for physical reason cannot interpret. Diverging solutions are not physically interpretable, so we have to take these solutions once our model extends down to the very center of the star. At the surface of the star, at the photosphere, the boundary conditions are ambiguous because the boundary of our model is not the physical boundary of the star, and so these are ambiguous, and some reasonable boundary conditions consist of adopting Stefan Boltzmann's law, because the outer boundary is the photosphere. The linearized version of Stefan Boltzmann's law is L given by the Lagrangian displacement plus the temperature, and another condition would be to require a force-free boundary condition, which means that the Lagrangian pressure perturbation is zero there. Okay, now if we have done all this work, and we might ask ourselves, like a mathematician, can we solve this system? And well, the mathematician's answer would be no, you don't have a solution. So what a pity, we have done all this work and a mathematician comes and tells you there is no solution to your problem. Well, we have one addition, we have in our system, we have one parameter which is still not fixed here. This is the eigenfrequency, and the question arises whether we could adjust this eigenfrequency in a way to guarantee a solution. Then we would have done two things at once. We would have guaranteed the solution of our system, and the second one would be we know something about our eigenfrequency. It's still undetermined, and once we know our eigenfrequency, we know the time dependence or the time behavior of our system. So if this could be done together, this would be quite nice. We guarantee that we have a solution. This is what would be one thing, and the second one, we get some information about our eigenfrequency. Okay, so, well, let's consider the solution problem of our system. Once we take all our conditions at either the inner or outer boundary, once we could do this, taking all four conditions either at the inner boundary or at the outer boundary, then we know that we always have a solution. This is a typical initial value problem, specifying all conditions at one boundary and then starting to integrate in a unique way from one boundary to somewhere else. The question or the problem here is that the boundary conditions are distributed between two boundaries, and in that case, in general, we do not have a solution. So there is a basic difference between an initial value problem for the same equations. We consider the same equations, but in one case, the boundary conditions are given all at one point. All four ones are at one point. We do always have a solution. And if they are distributed between two different boundaries, then in general, we will not have a solution. Well, to illustrate, this is a rather counterintuitive system here, and in order to illustrate the situation and how we proceed, the strategy of deriving eigenvalues, determining the eigenvalues, and at the same time guaranteeing the solutions of a solution of the problem, I would like to give you an example, a very simple example where everything can be done analytically. This can be done only numerically, and in that case we may get an impression or get a feeling what's going on here, what solvability of the system means as a boundary eigenvalue problem, and how we determine then the eigenvalues at the same time as we guarantee that the system has a solution. The system which we had in mind was our analogon of the pulsating star, which is the organ pipe of length L, and we have considered which are the equations which govern small perturbations of the configuration of an organ pipe of length L, constant pressure, constant density within our organ pipe. It is similar to the star. It's a one-dimensional acoustic configuration. Our star is a one-dimensional configuration. The organ pipe is also a one-dimensional acoustic configuration. We choose independent Eulerian variables x and t. X is going along the length of the organ pipe, and time t, of course, is the second parameter. Well, we have then done Eulerian perturbations of the background configuration, which is very simple in that case. Everything is constant here. And we have considered first, of course, the mass, the perturbation of the mass conservation equation, which in this case gives the Eulerian derivative of the Eulerian perturbation of the density. A tilde means Eulerian perturbation, and we have the divergence of rho times v reduces to d by dx rho 0, which is the background, the the stationary density times the velocity perturbation. Similarly, we have perturbed the momentum equation. On the left-hand side, this is the acceleration. This is the perturbation of the pressure, and we have related then the pressure perturbation to the density perturbation. Differentiate this equation once with time, with respect to time, and in the end we are left with the typical one-dimensional acoustic wave equation, which tells us that the second time derivative of the velocity perturbation minus sound speed squared times this second spatial derivative of the velocity perturbation is 0. So this is concerning the spatial variables. Concerning the time variable, it's of second order. That coincides with our stellar model. We have the acceleration in our perturbation equations, which gives a second order derivative with respect to time. So that seems to coincide both for the organ pipe and the spherically symmetric perturbation of the star. But here we have a second order spatial derivative, whereas in the full system, in the system describing radial pulsations of the star, we have a fourth order system. So what is different here? Which equations have not been considered here, which have been considered for our stellar configuration? Well, in the star we have considered mass conservation, momentum conservation, and pardon? Energy conservation and energy transport. This has been disregarded here, and therefore we arrive at a second order system. But how did we deal with the thermodynamics here? We somehow got rid of the entire thermodynamics, but somewhere it must be hidden. So we have done something with the thermodynamics of the system. What did we do with the thermodynamic aspects of the problem for the organ pipe? Where is the thermodynamics? Where did it go? No thermodynamic equations here, no energy conservation, no energy transport. But somehow the system must at least take into account, in a certain sense, it must take into account the thermodynamics. Well, it enters here, where we relate the pressure perturbation to the density perturbation. In principle, I should have said something about how this derivative of pressure with respect to density should be taken. Well, what we did here, I did not specify which quantity needs to be kept constant here, because in general you have that, I have to talk here. In general, the pressure is a function of density and temperature, or pressure may be written as a function of density and entropy and so on. So in principle, from a thermodynamic point of view, there has to be a second parameter. And here I have, without saying anything, I have taken the derivative of pressure with respect to density without considering a second dependence. Well, this can be realized either by saying, well, I keep the temperature constant or I keep the entropy constant. Then this derivative would have to be taken at constant temperature or constant entropy, and this means then this derivative, having constant entropy or constant temperature, would then correspond to the square of the isothermal sound speed or the adiabatic sound speed. Usually it's the adiabatic sound speed, because the changes of state within a sound wave are fast compared. The mechanical changes are fast compared to the thermal exchange of mass elements with its surroundings. So we have in some sense we have hidden the entire thermodynamics in this relation between the pressure perturbation and the density perturbation. So it's not really abandoned, but it's hidden somewhere here in the derivation of this equation. Okay, so we have this one-dimensional acoustic wave equation which should describe small perturbation within our organ pipe. Okay, here we are. Okay, like our stellar system, like our pulsating star, of course we have to have boundary conditions for this equation. So we need two boundary conditions because this is an equation of second order in the spatial variables. Well, we have an organ pipe which extends from x equal to 0, it's the bottom boundary, to x equal L, which is the top boundary of our organ pipe. And well, if we confine our organ pipe with rigid walls, then a rigid wall would require that the velocity perturbation should be 0 there, because it cannot move. There is a rigid wall. Then the velocity perturbation should be 0 both at the bottom and the top boundary. We have the same situation as in our star. The boundary conditions are not given at one boundary, but they are distributed between the bottom boundary and the top boundary. Similar situation as in our star. If we put all the boundary conditions at one place, at x equal to 0 or at x equal to L, we will always have a solution. But in the case when we distribute these boundary conditions between the two boundaries, there is likely to be no solution of the problem. Okay, we'll do also the same as we did with the time in our star. We separate the time dependence in the same way as we did it for our star. So we write that the Eulerian perturbation of velocity is given by some function which only contains the spatial dependence times an exponential in time containing some free parameter which we call, similar to our pulsating star, which we call the eigenfrequency omega in this time, in this place. So we write the time dependence as an exponential of I omega t. Well, why could we do this? Why does this lead to a solution? Here it is pretty obvious. Well, differentiation of the exponential gives the exponential times I omega, and here we have a second derivative with respect to time. This gives a minus omega squared, and all these functions contain the exponential, so we can cancel this exponential. But what is the requirement to do that? Is there a requirement on the sound speed? What would happen if one of the coefficients would depend on time? Then this separation is no longer possible. So one of the basic requirements to be able to separate the time is the independence of time of the coefficients of the differential equations. This was also true for our stellar system, because all the coefficients were dependent on the background model, and the background model is time independent, so all the coefficients are independent of time, and that's the reason why we can separate out the time dependence here. Okay, so we did everything in analogy to our stellar pulsations: time separation, boundary conditions, separate or distributed between the two boundaries. So we have, as a result, we have a boundary eigenvalue problem. It's called a boundary eigenvalue problem, containing a free parameter which can be adjusted to guarantee a solution. We have a boundary value problem because we have two boundaries at which the boundary conditions are given. And we may take the freedom in the eigenfrequency to guarantee a solution, and at the same time to determine for which values of omega we actually get a solution of the problem. Okay. Now here we are in a nice situation that we have an analytical solution of the problem. So we have to solve this second order equation in the independent variable x, where all coefficients are constant. The sound speed is constant, and also, of course, omega is constant. Well, so we have a second order equation with constant coefficients, and you all know the solution of a second order equation with constant coefficients. This is also an exponential. Okay, we'll come to that in a minute. Here is I have summarized what I already said. Well, for two boundary conditions at x equals 0, x equal to L, we have an initial value problem solution exists for arbitrary omega. If they are distributed, then in general there is no solution, and we adjust now omega to enable a solution, and we have a boundary eigenvalue problem. So the solution of these second order equation with constant coefficient is an exponential, and we write it in the form V hat is proportional to exponential ikx. If we insert this into our equation, then we have minus omega squared. Of course, the V hat, the constant or the exponential can be eliminated simply because the exponential is contained in any of these terms, and the second derivative of the function ikx here with respect to x, this gives a factor ik squared, this derivative, so this gives minus k squared, and here it's a plus c sound squared k squared, and the exponential is contained both in this term and this term, so it cancels. So we are left with a so-called dispersion relation. A dispersion relation is a relation of the frequency, the eigenfrequency, and this here is, so to say, a wave number. K has the character of a wave number, so the relation between the frequency and wave number or wavelength is called a dispersion relation. So we have a relation between omega squared and k squared, and we can solve this dispersion relation for the value of the wave number k. We see this is a quadratic equation, and it means we have two solutions, and we can write down the solution explicitly. K squared is omega squared over the sound speed squared, and we have two solutions plus, minus, and k, because we have a quadratic equation. So the most general form of the solution of the one-dimensional. Oops. Where do you? Okay, the most general form of the solution, the spatial dependence of the solution would be V hat is an integration constant times e to ikx plus a second constant times e to minus ikx. What is it physically? What does it mean physically? This part of the solution, if you take in addition, if you add the time dependence e to ia omega, what does it mean? Plus k minus k, what does it physically represent? One, it's a wave going left and the other wave goes right. So these are two waves going in opposite direction. And now we apply the boundary conditions. The boundary condition at x equal to 0, then the exponential, the argument of the exponentials is 0 and the exponential is 1. So the boundary condition at the bottom boundary of our organ pipe means that C1 plus C2 should be 0. Okay, let's take the other boundary conditions at x equal to L. Then we have 0 is C1 times e to ik L. L is the length of our, or the position of the top boundary, or is the length of our pipe, plus C2 times E2 minus IKL. If we consider, or if we apply or use that C1 is equal to minus C2, then we get a minus here, and we can cancel the integration constants anyway. So taking these two together, then we would have replacing C1 by C2, and then cancelling or dividing by C2, we are left with 0 is e to IKL minus e2 minus IKL. Now we bring this factor here, and we are left with a small manipulation of this equation. We are left with e to 2 times IKL should be equal to 1. 1 in the complex plane is not unique. You know, in the complex plane, here you have imaginary axis and the real axis. You have the unit circle, and here you have 1, and you can represent 1 is e to 2 I times 2 p n, 2 pi n. It's known to everybody. It's simple complex algebra, so we can write 1 is e to exponential of I times 2 pi n, and n can take on values 0, 1, 2. You can go round and round and round around the unit circle and get always 1, and you may represent it that way. So that means if we take the logarithm of that, well, it means that KL is equal to pi times n. And now inserting this again into our dispersion relation. What's going on? Okay. Can I continue? Okay. So this means we have now found an expression for the wave number k. K can only take on discrete values discrete values given by pi times n over L. So you have our boundary conditions restrict the possible values of k. So that means the system is only solvable, or has only a solution for discrete, of course an infinite number of discrete values of the wave number k. K can take on values pi times n over L. Now using our dispersion relation, this means omega squared is related to k squared. This means omega squared, our eigenfrequency, is sound speed squared times the possible value of k, which is pi squared n squared over L squared. That means we have a solution of the problem only for discrete values of omega, and only then we can guarantee that we can satisfy both the boundary condition at the bottom and the top of our organ pipe. And the same will happen now for our star. The same situation happens for our star. We can have a solution of the problem, the solution meaning solution of the differential equation plus the boundary conditions, only for a certain number of eigenfrequencies, and the eigenfrequencies, so to say, are determined by the boundary conditions. So the eigenfrequencies are determined by the condition that we can construct a solution of the problem. This example, this analytical example, should make this a bit more intuitive, so that you know what you are doing once you are solving the numerical by a numerical scheme. You are solving this boundary eigenvalue problem for radial pulsations of a star. Is that okay? Does it help in understanding or getting some feeling what's going on here? The organ pipe is the same that's going on once we consider the solution of the perturbation problem for radial pulsations. Okay? You have to go through that step by step once again, but it can all be done analytically, and you can understand each step. And you can see how the solution is constructed, that two boundary conditions distributed between the bottom and the top of the pipe will lead only to a solution in certain, or with only a solution for certain discrete numbers of the eigenfrequency. Okay. Okay, this, well, it tells you, you also get the solution. Well, the n equals 0 is the basic tone of the organ pipe. N equals 1 is the first overtone, 2 is the second overtone, and so on. Okay, solutions of the equation together with the boundary conditions do only exist for a discrete set of eigenvalues or eigenfrequencies. That's what we expect now also for our star. We expect a discrete spectrum of eigenfrequencies due to the solvability conditions, and we would like, of course, to know the eigenfrequencies of the stellar pulsations. In this case of stellar pulsations, we do not only have a real part of the eigenfrequency, but we do also admit an imaginary part, which tells us something about the damping of a mode or about instability or excitation of a mode. Here in that case, of course, it's a neutrally stable situation. In this case, the eigenfrequency is purely real. There is no imaginary part. These are neutrally stable oscillations of an organ pipe. Okay, there is one point left here, one issue we haven't considered yet in our equations, which is due to one of the coefficients of our system. Well, so far we have discussed the coefficient C3. This describes the stratification of density. Then the C4 is essentially a ratio between the sound speed squared and the gravitational potential energy. So that needs to be somehow be reflected in the coefficients of the perturbation equation, because these are sound waves and they have to be controlled by the stratification of the sound speed. There is one additional coefficient which we have not yet been considering. Well, apart from the 1 over r squared divergence of C1 and C4, all these coefficients C3 and C4 are of order unity. The only coefficient which deviates from that is the coefficient C1, and we need to consider this coefficient C1 a little bit more in detail. Let's go back to the definition of this C1. This actually varies a lot within the star. C1 is here it is. So it contains, well, these two contain only mechanical quantities. This is the sound speed squared. This is clear that this must be reflected in the coefficients. But this coefficient obviously contains also thermal quantities. In the first place, it's the luminosity, and then also one coefficient of the equation of state. The delta is contained in this coefficient C1. Okay, let's consider what this coefficient C1 really means, how this can be interpreted in physical within physical terms. Okay, and to do this, we first consider the thermal and dynamical time scale in a local sense. So far we have considered the dynamical time scale and the thermal time scale of a star in a global sense. That means we have taken the entire star to define either the dynamical time scale or the thermal time scale. Okay, so let's consider now, let's split our star into mass shells, and we would like to do you hear me? Okay, it's on again. Okay. Rather than considering the entire star for defining dynamical and thermal timescale, we consider now a mass shell within our star, which extends from R to R plus delta R. Well, how could we define dynamical and thermal timescale on the basis of a small piece of our star? Well, one way to define the dynamical timescale would be to ask what is the fastest signal which we can have in a star. This is a sound wave which crosses this mass shell of thickness delta R. So the dynamical timescale would be the sound travel time across our mass shell of thick delta R. Sound speed is given by sound speed squared is the ratio of pressure over density. Well, these estimates are only order of magnitude estimates, so numerical number of the order unity do not. Is it okay? Okay. It's it. Okay. Thanks. Okay, the time for a sound wave to cross would simply be the distance which we have to cross divided by the sound speed. So the dynamical time scale can then be defined by delta R, which is the thickness of the shell, times or divided by sound speed, which is the square root of p over rho, or divided by means the square root of rho over p. Okay, what would be the thermal time scale of this shell? Well, similar to the thermal time scale associated with the entire star, we could define it as the time needed to radiate away the thermal energy content of that shell at the local luminosity. So what we have to do is we calculate the energy content, the thermal energy content of that shell, and divide it by the luminosity. Then we have the time this element needs to radiate away its internal energy. So we have to calculate the heat content of this shell. Well, the energy content is given by the specific heat times the temperature times the mass of the shell. Thermal energy is given by specific heat times Okay, it's working again. If I switch on and off, it helps a little bit. Okay, so this is the heat content divided by the luminosity. This should be the okay. If it doesn't work any longer, then I speak without microphone. Okay, now we replace the delta m by the density and the volume of our element. So the delta m, the mass in our mass shell, will be of the order of density times the volume, and the volume of a spherical shell is the surface of the shell, 4 pi r squared times delta r. Okay, now we have two timescale, a dynamical timescale for our mass shell and a thermal timescale for our mass shell. Defined now not for the entire star, but for a single or thin mass shell within our star. Okay, well, the question is, are these two quantities well defined? We define it on the basis once. Now it will go, but I guess only for a while. Okay, these are ill-defined quantities because they depend on the quantity which we cannot determine, which is arbitrary. So these two timescales are, in that sense, they are arbitrary because the delta r is contained in both of these timescales. But if we take the ratio of these two, then the delta r will cancel, and we will end up with a proper definition, but not on the dynamical timescale and the thermal timescales themselves, but only on the ratio of both. So in a local sense, the dynamical and thermal timescale are ill-defined if they're taken separately, but if you take the ratio of these two quantities is well-defined quantity. So let's go to the ratio of dynamical and thermal timescale. Dynamical and thermal timescale depend on delta r, and we have a well-defined quantity which is the ratio of thermal and dynamical timescale, which is given then by the ratio of the quantities I have shown before. This is a well-defined quantity. Please keep that in mind. There are authors which use these local definitions of Okay. It works nicely. Thank you very much. Thank you very much. Okay. So we have well, I wanted to say there are authors which use these locally defined thermal and dynamical timescales separately, and they adjust the thickness of the shell according to their needs. This is not the right way to do it. You have to have a well-defined quantity, and this is only the ratio of these two. Whereas for the entire star, of course, we know how big the star is. There is a unique length scale which we should associate it with. This is the radius of the star. In the global sense, you can define both timescales separately. They are well-defined quantity because the radius of the star is, of course, well-defined. But within the star, in a local sense, the delta R, the thickness of the shell you should take, is not a well-defined quantity. So this is well-defined, and it gives the ratio of thermal and dynamical timescale. And once we now compare this quantity here, once we compare it to the coefficient C1, which appears in our perturbation problem, then we will find that the essential dependence of C1 on, say, the radius or the mass coordinate is essentially given by this ratio. So the coefficient C1 reflects the run of the ratio of thermal to dynamical timescale. Let us perhaps at this position give some. So in general, this ratio is small, close to the surface of the star, and it increases once we go into the star. And I would like to give you some examples for the run of the ratio of thermal to dynamical timescale. Here we have two stars. We have this ratio, the logarithm of this ratio, thermal to dynamical timescale, for two different stellar models. One of them is a Cepheid, and the other one is a hydrogen-deficient carbon star. Well, it is written as log 1 minus x. X is the relative radius. So we have the surface of the star is over here, and the center of the star is here. What you see in any case, what happens also in any star, this ratio of the thermal to the dynamical timescale increases by orders of magnitude once we go towards the center of the star, and once we approach the surface of the star. Of course, here the surface, or the region close to the surface, is expanded by this representation. So actually this is a much smaller domain, but to expand this regime where the ratio of thermal to dynamical timescale is low, we see here close to the surface this ratio is of order unity for the Cepheid, or it's even below order unity for the hydrogen deficient carbon star. So in any case, deep inside the star, thermal timescale to dynamical timescale is large, and close to the surface it may become of order unity or even less, depending on the stellar model. What does it mean once the thermal timescale becomes large? What does it mean? Pardon? Yes, that's true. If the thermal timescale becomes large, that means it takes a long time for the fluid element or for the mass element to exchange heat with its surroundings. That is the meaning of a large thermal timescale. So if we go inside the star, it will take a long time for the mass element to exchange heat with its surroundings, and that means no heat exchange with the surroundings means adiabatic changes of state. So the star becomes, or the perturbations become, not the star, the perturbations become adiabatic once we approach the center of the star. And they are non-adiabatic, or need deviations from adiabaticity need to be taken into account only close to the surface. And then we have to distinguish between stars where this region where the thermal timescale is small, or of, the ratio of the timescales is of order unity, where this region is small. This is for a Cepheid. So for a Cepheid, a large fraction of the star can be described by adiabatic perturbations, whereas for this hydrogen deficient carbon star, the domain where the thermal timescale compared to the dynamical timescale is low is much larger. In that case, we cannot expect that adiabatic perturbations are really a good approximation. So not for this one, and here the region is much smaller, where non-adiabaticity needs to be taken into account. This is for the hydrogen deficient carbon star, seems to be further off the adiabatic limit than the Cepheids. Okay, let's give you another example. Is the run of this timescale for two massive stars with same effective temperature and same luminosity but different mass. So we have a high mass object, it's same luminosity and same effective temperature, high mass and low mass object. Again, you see here, close to the center, or always if you approach the center, then this timescale is large. So we have adiabatic changes of states here, whereas once we go to the surface of the star, then this ratio drops below unity, either here for the 60 solar mass object at the outer 10% of the radii, whereas for the 24 solar mass star, it's of order unity or below in the outer 50% of the star. So this star will behave adiabatically more than the 24 solar mass, because the domain where the thermal timescale is high compared to the dynamical timescale is much larger than for the massive object. So it depends on how big the domain is where this ratio of thermal to dynamical timescale is of order unity or less. Okay? So these are the examples. And actually now this coefficient C1 is essentially this ratio, and therefore the thermal, or C1, is controlled by this ratio of the two timescales, the thermal to the dynamical timescale. So what is the consequence? Well, it means that the term in front of which, the bracketed term in front of which this coefficient C1 has to vanish. Okay, if we go towards the center, let's go back to the equations once again. Sorry. Okay, this is the equation where C1 is appearing. If C1 attains very large values, well, take it to the other side. 1 over C1 is small, then L dash should be finite. Then this means vanishing of C1 means that this bracketed term has to become small. And what does it mean if this bracketed term becomes small? Well, let's consider the pressure as a function of temperature, and for instance, pressure is in general a function of temperature and may be written also as in terms of the entropy. Then dP, if the entropy is constant, then P is a function as constant. That means P is a function of T, or d log, or the if we if we express the temperature variation in terms of temperature perturbation in terms of the pressure perturbation, then we have T1 over T naught is something like dt by the P at constant at constant entropy times P1 over P naught. That's simply taking assuming the perturbations of temperature and pressure, and so this is then this is P over T. So this is d log T by d log P at constant entropy, and this is the nabla adiabatic by definition. So this is in this notation, T is nabla adiabatic times P, and this is exactly what is meant by this bracketed term. So if this bracketed term vanishes, we have adiabatic changes of state. Okay, well, this was the time derivative of the entropy, and so what you see here, this is the deviations from adiabatic behavior which is left once this bracketed term is not zero. Okay, so we know T is nabla adiabatic times P, and in the case of adiabatic changes of state, and in that case this bracketed term will vanish. Then also, as a consequence, of course, then also the luminosity perturbations will vanish. There is no heat exchange with the surroundings, and therefore we don't have any luminosity perturbations. So another expression of constant entropy would be that this bracketed term is zero, or that temperature perturbations and pressure perturbations are related by the relation T is nabla adiabatic times P. Okay, so large values of C1 or large values of thermal timescale to dynamical timescale force that this bracketed term will become zero. As boundary conditions for R not equal to zero, because C1 diverges like 1 over R squared, we had that this bracketed term had to be zero as well. So just for regularity, this term has to vanish, but also if the coefficient becomes very large, then this bracketed term has to be close to zero. Okay, and this means we have adiabatic changes of state. So we have adiabatic changes of state for sufficiently deep layers. This is equivalent to the time derivative of the entropy becoming zero, or that the entropy becoming constant, or in other words, adiabatic changes of state. That means sufficiently deep in the star, the pulsations are adiabatic. T is nabla adiabatic times P. This is the condition, the explicit condition for constant entropy or adiabatic changes of state. Okay, well, what happens if we have adiabatic changes of state? Well, if we have adiabatic changes of state, the consequence is that we can abandon, by this relation, we can abandon all the thermal equations. Because you saw, if nabla adiabatic times nabla adiabatics T is equal to nabla adiabatic times P, then we also lose the luminosity perturbation. No heat exchange, no luminosity perturbation. So if we have no luminosity perturbation and the temperature is directly related to the pressure, then we can decouple the thermal and the mechanical equations. We can ignore the thermal equations because one of them is anyway satisfied. This is the energy conservation, and the energy transport is no longer needed because luminosity is 0. So what happens to the remaining mechanical equations? I have to go back here. Once we explicitly require temperature is nabla adiabatic times P, well, let's go to the equation once again. What we are left with is then, well, this equation is satisfied. Luminosity perturbation is 0. This equation is no longer needed because luminosity is gone. Well, there's only one place where the temperature is appearing here. Temperature appears in the mass conservation equation at this place. Now we know that temperature perturbation is given by the pressure perturbation is nabla adiabatic times P. Then we replace the temperature here by the pressure perturbation, and then we have the system decoupled. So the upper two equations do only contain the zeta and the P and are decoupled from the rest. So we can consider these upper two equations by themselves. The system is decoupled once we have adiabatic changes of state. And there is a transition to the full problem once the C1 is no longer infinite but has finite values, or once we consider the outer layers of a star. Okay, so we're left with a much simpler system describing adiabatic perturbations. Okay. In that case, we have the following. Okay, mechanical and thermal equations are decoupled and only the mechanical part is left. The first one is the mass conservation, where we have replaced the temperature by nabla adiabatic times P, and the second one is unchanged, which is the momentum conservation containing the remaining place where the eigenfrequency sigma appears. This is the acceleration term. So we are left with a second order system once we require adiabatic changes of state. Again, we need boundary conditions for this system. These are the boundary, these are now two boundary conditions because we have a second order system. There is again, or remaining, the regularity condition, which was present in the previous case. Just that in that case, well, C4 goes like 1 over r squared, so for at the center, this brackety term has to vanish. This is the analog of the previous regularity condition, 3 zeta plus alpha minus delta nabla adiabatic, which comes from the adiabatic changes of state. P times P is equal to 0. And we have to have one boundary condition left from the surface, which of course then would be the condition which requires a force-free boundary. So we have second order system, two boundary conditions, and again the frequency, the eigenfrequency as a free parameter in our differential system. Well, this is the case once C1 becomes pretty large. We could also go the way and say what happens if we require adiabatic changes of state over the entire star as an approximation. We know it's only an approximation because in any star the ratio of thermal to dynamical timescale becomes small, close to the surface of the star, and it increases inwards. So for the entire star it's certainly not a valid approximation. The question is to which degree will it be a reasonable approximation. For the Cepheid it might be a reasonable approximation because the region where the thermal timescales are small and non-adiabatic effects have to be taken into account. In that case, this region is small and the adiabatic approximation taken for the entire star may be a valid approximation. Not for the hydrogen deficient carbon star, where we saw that 50% or even more of the star is characterized by a low thermal dynamical timescale. Well, if we assume this adiabatic change of state for the entire star, of course, then this system would be valid for the complete star, and we could try to solve this system independently of the full non-adiabatic equation and see what the results will be. Okay, so these are at the same time not only those equations to which the general equations reduce in the case of getting close to the center of the star, but these are also the general equations for adiabatic, for the assumption of adiabatic changes of state, or this is the adiabatic approximation. These are the equations of the adiabatic approximation for the for adiabatic pulsations and adiabatic perturbations, adiabatic linear radial adiabatic pulsations and stability of a star. So at the same time we have now derived this approximation, which we shall deal in detail later on. So this is one of the valid approximations, or one of the possible approximations to the full non-radial, to the full radial non-adiabatic problem. So this is the reduced form for radial adiabatic pulsations and stability. Okay, I think now we are finished with the radial stuff, and in the next lecture we will start to consider non-radial perturbations around a spherically symmetric hydrostatic model. So see you. You say it's time. Okay. So next lecture we will go to the non-radial case. Thanks.
Yeah, thank you very much, Professor. So we'll have a short break of 15 minutes, and then we'll resume the session at 11:30. Okay, and I invite you for tea outside.
equations governing spherically symmetric radial perturbations around a spherically symmetric background model or hydrostatic model. We are now going to do the same, but without the restriction that the perturbations are spherically symmetric. We admit non-radial or non-spherical perturbations, and this means we are going now to the non-radial stability and pulsations equations. The strategy is very much the same as we did for the radial case. We start off from a spherically predetermined hydrostatic configuration, which does only depend on the mass coordinate or on spatial coordinate, but not on time. It's time independent and it's spherically symmetric. These are two important points for later. It's spherically symmetric and it is independent of time. It's a hydrostatic model and it satisfies the same condition and is constructed in the same way as before for the study of radial pulsations and perturbations. So we can assume that we know already, or the following quantities are predetermined and known. This is the radius r0 as a function of m, pressure, temperature, and so on. Now in hitherto we have only used the Lagrangian form of description. So we were always moving together with the fluid element, with the mass element. This is appropriate for one-dimensional systems, and it had the advantage that we could integrate Poisson's equation for the gravitational potential and give it in a closed algebraic form. This is no longer possible if we go to non-spherical perturbations. So what we have to do now is to solve the Poisson's equation explicitly. Well, of course, not for the hydrostatic model, this is a spherical symmetric model, but for the perturbations we have to invoke the full Poisson's equation, which complicates the system a little bit. Not very much, but a little bit. It increases the number, or it increases the order of the differential system, which for some people might be difficult, but we will see it's actually not that complicated and does not cause so many trouble. On the other hand, it's now, as we are going to non-spherical, non-radial, 3D perturbations, it's no longer advisable to use the Lagrangian description. It's more convenient to use the Eulerian description. So to say, we consider now our quantities as a function of radial or of position, and the position is our the position vector is our independent variable. So rather than writing r naught as a function of mr and rho and p as a function of mr, we replace it by function density as a function of radius, pressure as a function of density, and temperature. Of course, this can be done by simply rearranging variables in our models, which we have determined prior to the investigation of the stability and the perturbation. And we'll follow the same procedure as for the radial case, namely we linearize our general equations around this equilibrium. That means we take the mechanical and thermal equations as before, do the linearization as done for the radial case. Now we have to consider, in addition to the thermal and the mechanical equations, also Poisson's equation for the gravity. And we have to admit that we have now a three-dimensional perturbations. That means the perturbations do not only depend on the radius and the time, but also they depend on the angles theta and phi. It's convenient then to use spherical polar coordinates for describing the situations, and that means we write our quantity in the following form. So if we have a quantity q, this will now depend on three coordinates. This is a three-dimensional problem. It depends in spherical polar coordinates on the radial coordinate, on two angles theta and phi and on the time t. And similar to the radial case, we split this quantity into a hydrostatic time-independent spherical part, which we know. This has been determined by stellar evolution calculation, plus a perturbation part Q1, which now depends on all coordinates. So this is the same procedure as before. This term is the same as for the radial case, and Q1 now depends not only on r and t, like in the radial case, but on theta and phi as well. Okay. Well, I have said this already. In general, Eulerian perturbation, or the Eulerian picture, is much more convenient than the Lagrangian one. Okay, so, well, I have to add some remarks about Eulerian and Lagrangian picture again, because perturbations themselves may also be considered as being Lagrangian or Eulerian. What means Eulerian perturbation? Then we consider, in the case of an Eulerian perturbation, we consider the difference of the perturbed system and the original system at a fixed position in space and fixed time. So the independent variables in the Eulerian picture will be, the independent variables are the position vector and time t, and we consider a perturbed system and the original system. In the Lagrangian sense, perturbation means we consider a quantity in the perturbed Lagrangian. For the perturbed mass element, we focus on the mass element. The independent variable is the initial position vector of our element, and then it moves, this mass element moves to a new position r, which depends on the initial condition, and now we perturb this element. That means we perturb also the new position. So it's moved to another position, and the difference between the position in the unperturbed system and the perturbed system is called the Lagrangian displacement. So because we change the radius, or we change the position vector, we change, or we perturb also the position vector, and we have a difference between the actual position vector of the system in the unperturbed case and the position vector in the perturbed case. And of course, we relate the perturbed quantities also to the initial position vector of the mass element. So this, the different ways of looking at the system, co-moving observer or fixed observer in space, transfers also to the description of the perturbations, and we have to distinguish between co-moving perturbations and fixed perturbations. That means between Lagrangian perturbations and Eulerian perturbations. This is pretty important to distinguish between these perturbations. For instance, if we take a star and we take its surface or its photosphere, and we require that the pressure perturbation should be zero, or we don't want to have the pressure to be changed. So which pressure perturbation do we really mean? Do we mean the pressure perturbation at a fixed space, or do we mean the pressure perturbation once we move with the perturbation, or once we move with the fluid element? This is different, because in the case when you consider Lagrangian displacement, you follow, for instance, the distortion of the surface of the photosphere of the star. So what you require then would be, once you follow the distortion of the surface, you require that the pressure perturbation with respect to the perturbed quantity, perturbed surface, has to be zero. This is something different from sitting at a certain position. The surface of the star or the photosphere is distorted, and you ask that at this position the variation or the perturbation of the pressure should be zero. These are entirely different, and you have to think always which one of these perturbations, which kind of these perturbations have to be vanish or have to be continuous or what else. So it is not only a mathematical variety of describing the system. In some cases, one has to consider which one of the perturbations has to be considered, either a co-moving perturbation or a perturbation fixed in space. Okay. Okay, so we consider now not only two systems with two different descriptions, but we do also have, in addition, an original system and a perturbed system. So we have an unperturbed system, which is characterized by a quantity q or many quantities q, a position vector, either in the Lagrangian or a Lagrangian sense as a position vector depending on initial position vector, or in the Eulerian system just the position vector of a fixed position. And we have the perturbed system, q dash. The dash should denote a perturbed system, and we have, of course, in the Eulerian sense, we will not perturb the coordinate, the position vector r, but in the Lagrangian sense, of course, we will perturb the position of our mass element, which comes from the original position r0. Okay, so we have in the Lagrangian sense, an subscript L denotes in the Lagrangian sense, subscript E means in the Eulerian sense. So we have quantity Q in the unperturbed system depending on initial vector R0, and a position vector which depends now, which is the dependent variable for the Lagrangian system, which depends on R0 and T. And we have a perturbed system. Well, in the Lagrangian sense, we perturb the quantity QL dash, which depends on initial position vector and T, and the position vector itself is no longer an unperturbed quantity, so we perturb the position vector and end up with R dash, also depending on R0 and T. It's much simpler in the Eulerian picture. We have the unperturbed system depending on independent variables R and T, and we have the perturbed quantity Q E dash, which also depends on the position R and T. Now we have to identify the Eulerian and the Lagrangian quantities. Of course, the Lagrangian, this is the same as we discussed before, because the unperturbed system behaves like anything we have discussed in the previous lecture. Lagrangian quantity of the mass element, which is labeled by the initial vector R0, is equal to the Eulerian quantity of this mass element, which has moved from R0 to R. So this is the new position, or it's the actual position of this element. Now we have the perturbed quantities. That means the Lagrangian quantity, in the Lagrangian sense, quantity Q in the perturbed system, depending on the initial vector, is now equal to the Eulerian perturbation, or the Eulerian quantity in the perturbed system, but no longer at R, because the position of our mass element has also been changed and been perturbed to reach the position R dash. Okay. Now we define two variations or two perturbations. First, a perturbation in the Lagrangian sense. This means the differences between unperturbed and perturbed system for a fixed mass element. Lagrangian always refers to a fixed mass element, so it's denoted by capital delta. Delta Q is the quantity in Lagrangian sense in the perturbed system minus the quantity in Lagrangian sense in the unperturbed system. So it's QL dash minus QL, both taken at the initial position vector R0. And we have the so-called Lagrangian displacement, because in the Lagrangian sense, the radius vector or the position vector is a dependent quantity. So the delta R measures the distance between the position of the mass element in the perturbed system and the unperturbed system. So this is R dash depending on R naught minus the original position vector R as a function of R naught and T. This is called the Lagrangian displacement. Actually, we have used this Lagrangian displacement implicitly already in the consideration of the radial case, but I haven't said that this is Lagrangian displacement. It was the perturbation of radius. Perturbation of radius is nothing but Lagrangian displacement. Okay, in the Eulerian case, we denote the difference between the unperturbed or between the perturbed and the unperturbed system, so to say the Eulerian perturbations by A tilde. So these are the differences between perturbed and unperturbed system for fixed position vector. Pretty simple. This is QE dash minus QE at some fixed position R and T. Okay, what is the relation between these two? The question is, how can we calculate, or how can we transfer or transform from the Lagrangian perturbations to the Eulerian perturbations? What is the connection between these two? And to find this, we use the definition and try to get a relation between Lagrangian and Eulerian variation of a quantity Q. By definition, delta Q is QL dash minus QL at the position R naught. This is by definition. Well, this can be written as, well, this can be identified now with their Eulerian counterparts. Well, QL dash is equal to the Eulerian value once we consider that the mass element has moved in the Lagrangian sense to a new position R, and in addition it is perturbed. So this has to be taken at a position where the element has been moved and perturbed. So it's now at position R dash comma T, and whereas here it's pretty simple. For the unperturbed system, the mass element has moved from R0 to R, so we have to identify the quantities in the Eulerian and Lagrangian sense at the Eulerian coordinate R and at the Lagrangian coordinate R0. Okay? Now, now we use the definition, well, we keep this quantity, now we use the definition of Q tilde, the Eulerian perturbation. The Eulerian perturbation was QE dash minus QE, both at the position R. So we rewrite it in the following form. Then this is, it's Q tilde, this here is kept, and using the definition I showed you before, you can write it as Q tilde minus QE dash at the position R and T. It's just inserting here the definition of Q tilde and keeping the remaining terms. Okay, now we expand the R dash. We expand R dash here in the second term. This is Q tilde plus QE dash at the position R dash, which is R plus delta R. This is the original, the unperturbed position of our element, and this is the perturbation. So the new vector will be R plus delta R comma T minus QE dash at the position R and T. Now if delta R is small, we perform a Taylor expansion. This means this quantity here is Yes, this gives QE dash at the position R. This cancels with the second term, and the first term in the Taylor expansion is delta R times the gradient of QE dash at the position R. Simple Taylor expansion, and the first term in the expansion cancels. QE dash at R minus QE dash at R cancels. So this is the remainings. Now we have that we can, by definition, Q tilde is QE dash minus QE. We apply a gradient on this quantity. Then we may write this in following term. Gradient of QE dash is gradient of QE plus the gradient of the Eulerian perturbation Q tilde. Now we insert this gradient in here. Some question? Okay. Now we insert this gradient here, and we end up with some quantity QE. QE dash is gradient of QE plus gradient of Q tilde, but gradient Q tilde times delta R is a quantity of second order. We drop it. So we can write QE dash is simply the gradient of the quantity Q in the Eulerian sense, but for the unperturbed system. You agree? Okay, so we have found the following relation between Lagrangian and Eulerian perturbations. Well, it is delta Q, the Lagrangian variation of a quantity Q is equal to the Eulerian perturbation of this quantity plus the Lagrangian displacement vector times the gradient of the quantity Q in the Eulerian sense, still in the Eulerian sense, of the unperturbed system, because the Eulerian quantity is equal to the Lagrangian one, and we do not need to distinguish between these two. We can simply take this is the gradient of the quantity in the unperturbed system, which we know. For instance, our hydrostatic stellar model would then, or properties of the hydrostatic stellar model, would enter here through the gradient of the respective quantity. So it's simply delta Q is Q tilde plus Lagrangian displacement times the gradient of this quantity in the unperturbed system. Okay, once you mix both the Lagrangian and the Eulerian perturbation, and once you mix the Lagrangian and the Eulerian time derivatives, you have to be very careful, because these quantities in general do not commute. So d by dt delta q is not necessarily delta of dq by dt. So you have to satisfy, or have to obey certain of commutation rules. They are not commutative in general. Well, if you remain within your Eulerian or Lagrangian picture, it's nice. Then they commute with each other. For instance, d by dt is the Lagrangian time derivative acting on a Lagrangian perturbation of quantity q. Then by definition of the left-hand side, this is ql dash at position r naught by dt minus dql by dt at r naught. And this, on the other hand, is simply the definition of the Lagrangian displacement of dq by dt. So that's fine. And similarly, we have for the Eulerian perturbation and the Eulerian time derivative, this is the definition of d by dt of q tilde is simply qe dash minus qe and the partial derivative. And this, on the other hand, is the definition of the Eulerian perturbation of dq by dt. So we can commute these operations, perturbation and time derivative. Similarly, also the gradient acting on an Eulerian perturbation by definition is simply the difference of the perturbed system and the original system in the Eulerian sense acting with a gradient. This is simply the definition of the Eulerian perturbation of the gradient. So in these three operations commute, Eulerian perturbations commute with Eulerian differential operators, and Lagrangian perturbations commute with Lagrangian time derivatives. Well, if you mix these two, then this is no longer true. So you can, for instance, you can write down the Lagrangian derivative of an Eulerian perturbation Q tilde. Then this is Lagrangian derivative of QE dash minus QE in the Eulerian sense, both differentiated with respect to the Lagrangian time derivative. Well, the Lagrangian time derivative may be replaced by the Eulerian time derivative by the rule we know. This is d by dt, or in Eulerian sense, plus the velocity times the gradient of QE in the Eulerian sense, minus the same quantity for the unperturbed system. That's actually an error. It should be not V tilde, but V E with a vector. Please correct this here. This is a misprint here. So what we did, we simply applied d by dt. Lagrangian is d by dt Eulerian plus velocity times the nabla or gradient operator. So this is the result. On the other hand, we can evaluate the Eulerian perturbation of the Lagrangian derivative with respect to time of the quantity Q. So we have to put the tilde over the entire bracket here. So this d by dt Lagrangian is d by dt Eulerian plus velocity times the gradient of the quantity Q. The perturbation, the Eulerian perturbation of the entire bracket. So by definition, this is the quantity at the Eulerian perturbation of that quantity. This means it's d by dt QE dash in the perturbed system. Also, the velocity and the value of Q has to be taken in the perturbed system, minus the whole expression in the unperturbed system in the Eulerian sense. So this is now we replace the VE dash, the Eulerian perturbation, or the Eulerian value, not the Eulerian perturbation, it is the velocity in the framework of the Eulerian prescription in the perturbed system. So this is given by VE dash minus VE is simply the Eulerian perturbation of the velocity. So we replace it by the Eulerian perturbation of the velocity and the velocity in the unperturbed system. So that's what is left. This is VE, and we have to add another term here. This is the Eulerian. It's the Eulerian perturbation of the Eulerian velocity, or the velocity in the Eulerian scheme. It's too many expressions and too many notations for this quantity. So to get off this dash, we simply use the definition of the Eulerian velocity perturbation. Eulerian velocity perturbation is VE dash minus VE. So we end up with VE tilde here, and otherwise it remains the same. So dQE dash d by dt plus VE gradient QE dash, this remains the same, and by applying the definition of the Eulerian velocity perturbation, we get this additional term here. Now we compare the two let's do it first the other way. This is simply this is the Eulerian perturbation of the d by dt q tilde, what we have here, plus the velocity times qe dash is now replaced by the Eulerian perturbation of q and qe itself. So we have, this is v tilde times gradient qe plus gradient of the perturbation of q, Eulerian perturbation of q. So what we use is q here is q tilde is qe dash minus qe. So we replace the gradient qe dash here by gradient qe and gradient q tilde. So this is this term, and this here is by definition this is d by dt plus velocity times gradient d by dt minus d by dt plus velocity times gradient. This is simply d by dt in the Lagrangian sense of the difference between qe dash minus qe, which is d by dt Lagrangian by q tilde. Okay? This means now we have d by dt dq tilde by dq by dt perturbed Eulerian is d by dt of q tilde plus the velocity times the gradient of q, because this quantity here is of second order in the perturbation, so we can neglect this, and here we identify qe with ql, or in the general case with the quantity, the background quantity q naught. So in that case we have that the Eulerian perturbation of the Lagrangian derivative with respect to time of q is given by the Lagrangian derivative of the Eulerian perturbation plus an additional term, which is the Eulerian perturbation of the velocity times the gradient of the background of the original quantity. Okay, so you see that Eulerian perturbation and Lagrangian time derivative do not commute. There are extra terms. You need to take into account extra term to account for the no, it's not really incompatible, but it's not, they simply do not commute. You have to be careful if you mix different perturbations, Lagrangian and Eulerian perturbations, and different time derivatives, Eulerian and Lagrangian ones, then you may get additional terms. Well, similarly, the operator delta, the Lagrangian perturbation, and d by dt and nabla do not commute. So keep that in mind if you come across that situation. You have to calculate what is the relation between these quantities. As an example, which we might use later on, is the Eulerian velocity perturbation in relation to the Lagrangian displacement and to the Lagrangian velocity perturbation. So we would like to know the relation between the velocity perturbation either in the Eulerian sense or in the Lagrangian sense. So the Eulerian velocity perturbation is given by the Lagrangian velocity perturbation. Let's go up. Lagrangian velocity perturbation. This is the general form, the general relation we got. So we apply this. Delta q is equal to q tilde plus Lagrangian displacement times the gradient. We apply this to the velocity. This means the Eulerian velocity perturbation is equal to the Lagrangian velocity perturbation minus delta r times the gradient, or the divergence of the velocity field. That's the better formulation. So from the general relation between Lagrangian and Eulerian, perturbation, we get that the Eulerian velocity perturbation is equal to the Lagrangian velocity perturbation minus Lagrangian displacement vector times nabla acting on the background velocity field v. Now we know the velocity is the Lagrangian derivative with respect to time of the position vector in the Lagrangian sense. Now we know delta and d by dt commute, so this is d by dt of the Lagrangian displacement. Minus, of course, this term is kept. Well, now we replace d by dt Lagrangian of the Lagrangian displacement by the relation between Lagrangian time derivative and Eulerian time derivative, which is d by dt plus velocity times nabla acting on delta r on the Lagrangian displacement, and we are left with the final result of the relation between the velocity perturbation in the Eulerian sense related to the Lagrangian displacement. Eulerian velocity perturbation is d by dt in the Eulerian sense of the Lagrangian displacement plus velocity times nabla acting on the Lagrangian displacement delta r minus delta r times the nabla operator acting on the velocity field v. So this is a famous or often used relation between Eulerian velocity perturbations and Lagrangian displacement. Well, some authors even use mixture of Lagrangian and Eulerian perturbations just for convenience. Sometimes a variable might be better represented in the Eulerian formulation, and in other cases it might be considered in a more convenient way in the Lagrangian. So some authors use even mixture of Lagrangian and Eulerian perturbations. So far we have used only purely Lagrangian perturbations. We will, once we come to the non-radial pulsations, you will see that in some respect we also mix or have a mixture of both definitions of both approaches together. So I should warn you here, be careful whether you have Lagrangian displacement, Eulerian displacement, you have Lagrangian time derivatives, Eulerian time derivatives, you can easily get confused. Okay, that is a digression on a remark on the various perturbations. Well, now we are going to do the same as for the radial case. We will linearize the mechanical equations. However, contrary to the previous case, we will adopt the Eulerian point of view. Okay, we will use the mechanical equation in Eulerian form, and we will use Eulerian perturbations, contrary to the previous case where we have done it on the basis of the Lagrangian description. Well, first of all, in the Eulerian terms, or in the Eulerian momentum equation, we have this nonlinear term which goes with velocity times nabla time acting on the velocity field, because we are starting from a hydrostatic star which has no velocity field. The velocity field of the unperturbed configuration is 0. This term will be a first order in the perturbations anyway. So we drop this term from the beginning because it will be of first order. And also we will replace here the 1 by tilde because we are assuming, or we are using Eulerian perturbations. So this quadratic term will be neglected. So the only term in the acceleration, well, dv by dt is Eulerian dv by dt, and v0 is 0. We have a hydrostatic configuration. Then the d by dt of the velocity which remains is simply the Eulerian derivative with respect to time of the velocity components. any other of these components or any other of the terms can be neglected because they are of second order, or we have zero velocity field in our hydrostatic configuration. Now, the right-hand side of the momentum equation consists of the pressure gradient and the gradient of the potential, the gravitational potential. So gravitational potential occurs linearly within our equations. So this is written as phi naught plus phi tilde. But for the unperturbed quantity, we have equilibrium between the pressure gradient and the potential. So this will cancel, the unperturbed term will cancel with the gradient of the pressure. Therefore, we have omitted it from the beginning. The only case or the only places where we have to introduce the perturbation is, first of all, we have to perturb in the Eulerian way the pressure. The right-hand side is 1 over rho dp by dr. This gives, first of all, this unperturbed term plus a perturbation of the pressure minus 1 over rho 0 times dp tilde over dr. We only have kept here the unperturbed term because otherwise we would have a second order term in the perturbations. Again, all second order terms in the perturbations are neglected, and then we have to perturb the 1 over the density, and we have this is multiplied with the quantities in the unperturbed system, because otherwise we will again get a higher order term, and we get a 1 over rho perturbed. 1 over rho perturbed gives gives rho tilde divided by rho squared, and the dp by dr, as a coefficient we keep the dp naught by dr. So this is the linearly perturbed first component of the momentum equation. Of course, we have now not only one component, because we consider three-dimensional perturbations which also depend on angle theta and phi, and of course we at the same time we do not only have one component of the velocity vector but three components. Clear? Okay, there is no stationary counterpart for the theta and phi component of the momentum equations, so they become rather simple. The left-hand side is similar, the acceleration is similar to the left-hand side of the radial component. So this is the Eulerian perturbation of the theta component, and the phi component differentiated with respect to time t in the Eulerian sense. Then we have, because there is no dependence of the pressure of the stationary model with respect to theta and phi, it's only the perturbation of the pressure with respect to theta and phi. So the term corresponding to that one would be cancelled, because dp naught by d phi and dp naught by d theta is 0. So we have the corresponding or the counterpart of this term with respect to theta and phi derivatives. So this is 1 over rho times the gradient of pressure with respect to theta and phi, and similarly also the gradient of the potential or its components in theta and phi directions is 1 over r d phi by d theta, d phi tilde by d theta, and 1 over r sine theta, and the derivative of the perturbation, the Eulerian perturbation of the potential with respect to phi. Okay, this is the perturbation or the linearized version of our momentum equation, while the second equation which we need to consider for the mechanics is the continuity equation, of course. Well, the continuity equation, again, the velocity field in our stationary configuration is 0. The density, of course, is there and also has a gradient. So the perturbation I think you can, if you are interested, you can do it yourself. It's a little bit of algebra, simply saying rho is rho naught plus rho tilde. This means the density is split into the stationary and the stationary part and the perturbation, and then expand everything up to first order, and keeping only the first order term and neglecting higher order terms in the perturbation. So what we are left with is d rho tilde by dt plus the velocity in the radial component times the gradient of the background model with respect to r. D rho naught by d theta and d phi is 0, therefore corresponding terms associated with the velocity components with theta and with phi are not present. And then we have essentially the divergence of the velocity field in the second term. This is rho tilde times the rho 0 times the first order term in the velocity field. This is the divergence of the velocity field essentially in terms of radial and the two tangential components of the velocity field. So this is linearized version of the mass conservation, and of course now we have also to consider, in addition to these two equations, we have to consider the linearized version of Poisson's equation. Well, Poisson's equation is itself linear, so we just need to take the perturbations of the perturbations of the potential, and we only need to keep the perturbations at any place. So this is, in principle, this is 4 pi g times rho naught plus rho tilde, but on the left hand side the Laplace operator on the stationary potential is 4 pi g times rho naught, so these two terms cancel, and we have left the linearized version, or the Laplace operator acting on the potential, the Eulerian potential perturbation, which is equal, according to Poisson's equation, which is equal to 4 pi g times the Eulerian density perturbation. So this is now a much more complicated version of the mechanical equations. We still have mass conservation and momentum equation, but in addition to that we have the equation for the gravitational potential. Okay, so what shall we do to get it to give it a bit simpler form is we differentiate the mass conservation equation with respect to t, then we get a second order derivative with respect to time for the density, and first order derivatives with respect to time for the velocities. So dvr tilde by dr, here we get another dvr tilde by dt, and here we get first order time derivatives with respect to the components v theta and v phi, and for vr and v phi. And these can be used, or this can be replaced by the second and third components of the momentum equations. So we have the expressions for dv theta tilde by dt and dv phi tilde by dt. We insert this and eliminate the velocity components v theta and v phi. So this differentiation and inserting the results gives or makes the situation much more convenient. So what is the result then, which we are left with? Well, this is the form of the this is the form of the mass conservation equation. We have differentiated it with respect to t, and we have replaced the remaining time derivatives of the v theta and v phi component by the respective components of the momentum equation. And then we are left with an equation containing only the density perturbation, the pressure perturbation, the potential variation, and the radial velocity components. The two components v theta and v phi have been eliminated by this trick. So what is left then? Well, that's the first step. Now we need to linearize the thermal equations. That means we need to linearize the energy conservation equation and the equation for energy transport. I'm sorry, it's now a little bit, it's a lot of algebra we need to go through. But in the end, everything will be nice and it will collapse again to some nice equations. Okay, so the general form of the energy conservation equation is rho times T, now given it in the entropy formulation, and in the Eulerian picture, ds by dt times V times nabla acting on the entropy S is given by the energy generation term minus the divergence of the flux, which describes the energy deposition or taking of the energy once we have a heat flux in our system. Well, we do the linearization in the usual way. Here we certainly take into account the background model and we perturb everything in the usual way. Linearization means we expand it around the equilibrium and we neglect terms of order higher than 1. Okay, so the linearized version of the left-hand side looks like rho naught times T naught times the time derivative of the entropy of the Eulerian entropy variation plus the perturbed radial velocity component times the background entropy gradient. Well, this is now, well, first of all, the term rho times epsilon looks very much the same as in the radial case. There is no difference, but the divergence of the flux is now, of course, much more complicated because we do not only have one component of the flux, we have 3 components of the flux, and the divergence must be written. Fortunately, it's a linear term, so we don't need to expand anything. So the divergence of the flux involves two terms with the radial, with the Eulerian perturbation of the radial component of the flux, and of course components which involve the theta and phi components of the flux. Okay, now we have used the background. Of course, we have implicitly used the relations for the background. Well, now next step would be to linearize the equation of energy transport. This, of course, now does not have only one component, but it has 3 components. Oops, so this is a little bit of work, but we have done it immediately. I promise you we will. Okay, thanks. Well, the linearization of the radial component is very much the same as we did it in the radial case. So we have a radial temperature gradient in the background model, which needs to be accounted for. We have a perturbation, and we have the perturbation of the diffusion coefficient. The diffusion coefficient very much like the radial case. So this contributes via the perturbation of the opacity and via the perturbation of the density, very much like the radial case. The 1 over T cubed is accounted for by this term, and we have, of course, taken into account that for the background flux and the background temperature gradient, we have a special equation which needs to be satisfied separately. So this equation looks very much like the equation we have already had, But we have two additional equations, and we observe, or we take into account, that the stationary component of the flux in phi and theta directions are 0. So we can take the following. We can take the diffusion coefficient to be the unperturbed quantity. Everything here is given by the unperturbed diffusion coefficient, and only here, once we expand into first order, we relate the phi component of the perturbation of the flux with the phi component of the temperature gradient of the temperature perturbation. So we have these two equations in addition. What shall we do with it? We get rid of them actually. We get rid of the flux components in the theta and phi direction by inserting them into our energy conservation equation, which was the one above here. Okay, here we have the divergence of the flux, and we insert for f theta tilde and f phi tilde, we insert the values given from or presented by the theta and phi component of the energy transport equations. So we can eliminate these quantities simply by applying the second and third component, and thereby we get rid of this equation and we get rid of the variables. So it starts to collapse already. The system of equations become smaller and smaller. So if we do this, just 2 minutes. Where is the mouse? Sorry. It seemed to stop working. Okay, now it works. Okay, so sorry, I would like to go up. Okay, now we have replaced in this. In addition, we introduced, like in the spherically symmetric approach, we replaced the perturbation of the radial component by the luminosity perturbation, and we end up with an equation, with an energy equation of the form which contains only the gradient of the luminosity perturbation, and then instead of keeping all the components, theta and phi components of the flux, we have a second order derivative acting on the temperature Eulerian temperature perturbation as in addition to what we had originally in our radial case, whereas the perturbation of the energy transport equation is almost identical to the radial case. These terms appear in the radial case and also this one, so there is not much difference between the radial and the non-radial case for the energy transport, whereas for the energy conservation there is an additional term here involving theta and phi derivatives with respect to the temperature here. So these are the results for the thermal equations, and possibly okay. And the result for the mechanical equations is we have the perturb equation for the for the potential, and we have an equation for the perturbation of the momentum, for the combined momentum and mass conservation equation, which is this one. Okay, let's finish with the discussion of that this afternoon. So what we'll need to do, we want to give these equations, which seem to be rather complicated. It's a partial differential equation with respect to three spatially independent variables and one time variable, and we would like to reduce its complexity and its size down to a size which is similar to that which we got for the radial case. This will be done this afternoon, and then hopefully we finish with all that mathematical, nasty mathematical stuff here. Thank you very much. Good afternoon, everybody, and welcome back. This morning we have considered the equations governing small non-radial perturbations around the spherical hydrostatic equilibrium, and we derived by linearization equations for these small perturbations in terms of Eulerian perturbations of velocity, pressure, density, and so on. So the equations we were deriving is first of all here the radial component of the momentum equation. This is the first line, the first equation. Then we have taken the second and third component to eliminate these velocity components or the Eulerian perturbations of these velocity components, and arrived at the version of the mass conservation. This is this equation. So we observe some well-known terms from the radial case, which we studied before, and we observe that the derivatives with respect to the angles theta and phi occur only once we inserted or eliminated the theta and phi components of the velocity. They occur only in certain combinations. So we see we have the second derivative with respect to theta of the pressure perturbation plus 1 over sine squared theta times the second derivative of the pressure perturbation with respect to the angle phi plus cotang theta times the first derivative of the pressure perturbation by d theta. The same combination of the angular derivatives is found for the potential here. So these are the same combinations of the derivatives with respect to the angles theta and phi. Now let's go on. The next equation, or the results for the next equation, this is the energy equation and the equation for energy transport. Well, the first part is a little bit familiar already from the radial case, but there is an additional term involving the theta and phi derivatives, and actually it's exactly the same combination of the theta and phi components as before, acting here on the temperature perturbation, which have been acting before on the potential and on the pressure perturbation. So keep in mind, only these combinations of the angular derivatives appear in the perturbation equations. Finally, the perturbation or the linearized version of the energy transport equation looks very much like its counterpart for the radial perturbations. Well, in addition to momentum, mass conservation, and energy transport, we have to solve the Poisson's equation for the potential, because for the non-radial case we cannot solve this implicitly like in the radial case. Let's have a look whether we have the well, for the Poisson's equation we also see this. We have the second derivatives with respect to theta, then 1 over sine squared second derivative with respect to the angle phi plus cotangents theta, the first times the first derivative with respect to theta acting on our potential perturbation phi. So always the same combination of angular derivatives appear in this equation. Okay, how can we use, or how can we make convenient use of this fact? So we observe finally that all these linearized versions of the equations we consider, they contain differential operators containing the derivatives with respect to theta and phi only in the combination second derivative with respect to theta plus 1 over sine squared theta second derivative with respect to phi plus cotangent theta times first derivative with respect to theta. Let's call this operator, this is a two-dimensional operator or an operator which acts on a two-dimensional field. Let's call this minus L squared, and maybe with this notation you may be already suspecting what this means or what this operator might be interpreted with. Do you know this operator L squared? Remember quantum mechanics? Does anybody? What? Pardon? It's the angular momentum. It's the angular momentum operator which is known from quantum mechanics. Well, quantum mechanics has an extensive literature on all these angular momentum operators, and a representation in space of the angular momentum operator is actually this second order derivative with respect to the angles theta and phi. Okay, how can we make use of our discovery that we have the quantum mechanic angular momentum operator here in our system? Well, we know the properties of the angular momentum operator because we know the eigenfunction of the angular momentum operator. The eigenfunctions of these operators are the spherical harmonics YLM. This is a series, or these are functions, spherical harmonics, which depend on two indices, L and M, and are functions of theta and phi. So these form a complete orthonormal system. You may know what this is from quantum mechanics. A complete orthonormal system, that means we can expand any function of theta and phi in terms of these spherical harmonics, and we can represent completely any function of theta and phi by a sum over, an infinite sum over the spherical harmonics. So we may represent any of our perturbations, Q1 or Q tilde, as a function of r and t and theta and phi as a sum over coefficients Q1 Lm. These now have an index or have a subscript L and M hat, meaning that these only depend on radius and time, times the spherical harmonic YLM only depending on theta and phi. And this is to be taken as an infinite sum over the indices L and M. So what did we achieve by this, by writing it in that way? What did we achieve? Well, we have separated in some sense the RT dependence from the theta and phi dependence. Okay, so we have gained by this trick, we have gained a separation of variables. Okay, now we make use of the fact that the YLMs are the eigenfunctions of the angular momentum operator. That means L squared acting on YLM is simply L times L plus 1, where L is the harmonic degree and is one of these indices of the spherical harmonic YLM. So we can write L squared acting on YLM is L times L plus 1. This is the eigenvalue of the operator L times the times the function Lm. So this operator will not mix different spherical harmonics. Acting on one spherical harmonic, it reproduces the same spherical harmonics with a factor L times L plus 1. It does not mix different spherical harmonics. Okay, so what we have achieved by writing it in this infinite sum, we have achieved a separation of the angular variables, and well, the disadvantage, we have got a an additional parameter in our equations, which is the harmonic degree. Okay, so we have at the cost of an additional harmonic, of an additional parameter, L, which is the harmonic degree, we have separated the angular dependencies, and we have an additional parameter in the remaining partial differential equations, which are partial differential equations in the radial variable and the time variable. Okay, so what we have in principle, because the YLMs form a complete orthonormal system, we have reduced the partial, or we have transformed the partial differential equation in R, T, theta, phi into an infinite set of partial differential equations in R and T with a parameter L. Okay? Well, the fact that we only have L squared as an operator which acts on the angle theta and phi, this means that we don't have a mixture, a confusion or a mixture between the different YLM components. So we have a system of completely independent, by this trick or by this expansion, we have a set of infinitely many partial differential equations containing an index L, but we have lost the angular dependence at the cost of having an infinite set of equations. That okay? So they separate, all these equations are separate and independent because the YLMs are not mixed through the operator L squared, and because they are linearly independent, so we can simply separate each component of YLM, and the coefficient of the YLM occurring in the infinite sum over the harmonic, over the spherical harmonics, it may be separated into various equations, one equation per coefficient of an YLM function. Okay, so for simplicity, again, we omit the hat, which we have introduced here, because now we know the function q, which is given in our equation, should in principle have a hat and should in principle have an index or a subscript Lm, but for simplicity we omit this, keeping in mind that of course these quantities will then depend on the harmonic degree L, but no longer on the angle theta and phi. So let's go to the equation and see what happens. Well, the first equation remains essentially unchanged. If we compare it to the original version, we have let's go to the original version. So not much has to be done. So this is the original version. We take each of these quantities, each of the dependent variables, expand them in terms of spherical harmonics. Now, because the spherical harmonics are orthogonal and linearly independent, so this equation has to be valid for each component, for each coefficient of a spherical harmonic. Nothing happens because there is no derivative with respect to the angles there. What about the next equation, which is the mass conservation? Well, in this case, nothing happens because the YLMs are linearly independent. And here we have the operator L squared acting on the spherical harmonics as well as here, but the operator L squared does not mix the spherical harmonics. So this gives this expression acting on a YLM gives L times L plus 1 times the spherical harmonics. So this and this part, each of them gives L times L plus 1 times the the Eulerian pressure perturbation or the Eulerian perturbation of the gravitational potential. So these big expressions reduce to L times L plus 1 times the perturbed pressure and the perturbed gravitational potential. Okay, so the same will happen for the energy equation. Well, here, first of all, we have the potential equation. So this part of the Laplace operator from here to here is nothing but L times L plus 1 over R squared times phi tilde. And then the next one would be here. This is this result here. We have the L squared operator also appearing here in the energy conservation equation. This is L squared acting on T tilde, acting on the spherical harmonics, gives L times L plus 1 times T tilde. And the last one, again, does not contain any derivative with respect to the angle, so this remains unchanged. So we are left with, in the end, with the following system of equations. Well, first of all, the momentum equation, what's remaining from the momentum equation, then the mass conservation equation appear with an L times L plus 1 appearing here, times P tilde plus rho naught times phi tilde. Then we have the Poisson's equation for the potential, and the angular dependencies have disappeared or are condensed in this L times L plus 1 over R squared times phi tilde is equal to 4 pi g rho tilde. Okay, then for the energy conservation equation, we have the first part, which reminds us of the radial problem, plus a term which goes like L times L plus 1 over R squared times the perturbation of the temperature. And finally, the last equation then is the perturbed or the linearized version of the energy transport equation. So it looks very much like the radial problem, but we have an equation for the potential in addition, because the potential cannot be solved implicitly and algebraic in an algebraic form. We have to solve this equation separately or in addition to the other equations. Momentum, mass conservation, energy transport, plus here in this case the equation for the gravitational potential. Well, in addition to these equations, we have, of course, the equations which the stationary or the hydrostatic variables satisfy. This means gravitational hydrostatic equilibrium. It means that for the stationary potential, of course, also Poisson's equation is valid, and that for the stationary configuration, for the hydrostatic configuration, luminosity is given essentially by the diffusion coefficient and the temperature gradient, and also that the run of the luminosity with radius is determined by the nuclear energy generation rate. Keep in mind this. Keep in mind that actually this represents these equations are not really single equations, but they represent an infinite set of equations. For each value of L, we have a single equation, and this is an infinite sequence of equations, or we can consider it as a parameter of the equation and solve the equation for each parameter separately, or taking L, the harmonic degree, as a continuous parameter. So we have a one parametric infinite number of equations, or we have one set, or we may regard it alternatively as an equation with a parameter which has to be solved for any value of the harmonic degree. So this is still a partial differential equation containing the radius and the time as independent variables. Well, all the coefficients of this equation seem to be independent of time. They only depend on the background, on the hydrostatic model, which we have defined before this analysis. So all the coefficients of these equations are time independent. Therefore, we do the same procedure as for the radial case. We also separate not only the angular dependence, but also the time dependence in very much the same way as we did it for the radial perturbations of our hydrostatic star. Well, the question is, why is it possible to gain this separation of the angular dependence from the rest? What is actually necessary to guarantee that we can proceed by a expansion in terms of spherical harmonics and thus somehow remove or separate the angular dependence from the radial and the time dependence? What is actually necessary, or what does guarantee that we can do it in that way? Do you have an idea?
Coefficients are independent of the angular.
Yes, the reason is the coefficients are independent of the of the angles theta and phi. If they were depending on the angles theta and phi, then our expansion in terms of spherical harmonics would fail, or in other words, then the different components would mix. So then the operator, the angular momentum operator certainly does not mix the different spherical harmonics, but they would be mixed by an angular dependence of the coefficients. So if you take a rotating star which is flat, has no spherical symmetry, you could not do it by this simple expansion. So in the same way as we can separate the time dependence, because the coefficients are independent of time, we can separate the angular dependence because the coefficients of the differential equation are independent of the angle. So the spherical symmetry of our hydrostatic, spherical symmetry and time independence of our initial model of our hydrostatic model is essential to perform either time separation and the angular separation as it was done here. Okay, so let us perform the time dependence. Well, as for the radial problem, we assume that Q tilde is given by a only radially dependent part of the function Q times the exponential of I omega t, where I omega or omega is again the complex eigenfrequency of our system. By this approach we get a separation of time, and then we end up with a set of ordinary differential equations, because now the only independent variable is the radius or the position r. So we get a system of ordinary differential equations in R. So this is the final result with parameters. Parameters now is the harmonic degree and the eigenfrequency omega, as for the radial problem. And well, there is nothing to be done anymore except for preparing the resulting equations for a numerical treatment. And so as for the radial problem, we will measure the eigenfrequency in units of the dynamical timescale. We will normalize all quantities. We will go from the perturbations to the relative perturbations to get dimensionless quantities. This is one point. we will try to get all the coefficients of our equations dimensionless. And, well, in addition to that, this is a more technical point. Apart from going to the relative quantities, we have to consider what is the dependence of our variables once we go to r equals 0. Once we want to consider, or once we want to calculate a complete stellar model extending to the very center of the star, then it's for numerical reasons, not for analytical reason. For analytical reason, we do not need to do it, but we observe that, for instance, pressure perturbation, temperature perturbation, and the potential perturbation go to 0 with the power r to L. R to power L is the behavior of all these quantities once we go to 0 radius. That means all these quantities become 0 at the same time, and this 0 is a numerically ambiguous quantity. So if you say this, both pressure and temperature have to be 0, then this numerically the ratio then of pressure and temperature perturbation is not well defined. You take the 0 of two functions. Numerically, analytically, it's not a problem because the power r to L cancel, and then you have a finite ratio of these two. But numerically, this is pretty bad. We have a ratio of two quantities, which is 0. So the way a solution of the problem is to take out the behavior of the quantities once they approach 0. So to define a quantity p hat, which it does not suffer from this problem. So we take p hat, or we define the p quantity p hat by p tilde is equal to p hat times r to the power L. Then p hat will have a finite value once we approach the center. This is numerically more favorable rather than having quantities which disappear both at the same time, but their ratio is no longer defined. The ratio of p hat to t hat will be well defined even in the center because they are finite. So that's just a remark concerning the numerical treatment and a proper numerical representation, such that also the center of the star or the regions close to the center are numerically well behaved. Not analytically, it just refers to the numerics. Okay. Now, if we do that, and I don't want to go into the details, it's a lot of algebra and a lot of transformation which needs to be done, but this does not give too much of physical insight. We have already seen at the example of the radial case how this works and how this is done. Okay, so what we end up with is, well, now I have written here in this case, I have written it in terms of x, which is the relative radius, in terms of x as the independent variable. The equations which we get as the perturbation equation, or the linearized version of the momentum, mass conservation, energy transport plus potential equations. So what we end up with is a system of equation which partially looks quite similar to the radial case. It's not that simple, but there are some terms which we might recover. This is, for instance, alpha times p plus delta times t. This is a term which also appears in the radial case. There is another term which goes, well, no, this is not true. Well, these terms might be recovered. This is the mass conservation equation. Once we go to the next one, this is the momentum equation. You recover the acceleration here. This term is also present in the radial case. Well, the different form also comes from the fact that we have done several transformations and that we are in the Eulerian scheme. So the Eulerian scheme is more convenient in this case, but it also generates many more terms, and it becomes a little bit confusing. I don't want you to look at all these terms. It's just the result what we get once we apply all these transformations, these normalizations, and taking out the dependence of the variables once we go to r equals 0. It's a rather technical point, and most of these transformations are necessary or are motivated simply by a convenient numerical treatment. But the physics is not much different from that of the radial perturbation equations, apart from the occurrence of the harmonic degree as a new parameter. Okay, so this is mass conservation, the final result. Next one is momentum conservation. Then we have the energy conservation. You recover the I sigma term. This is where the time derivative of the entropy comes in. This is the condition if the bracket is 0. This means that the system behaves adiabatically. Well, there are many other terms. There we have somewhere should be the epsilon terms. Well, you have to search for them. Ah, here it is. Here are the epsilon terms. This is the perturbation of the energy generation rate. So this is the final form of the energy equation. Then, of course, we have the energy transport equation, which is, well, this looks more familiar than the other ones before. It contains the kappa p and kappa t terms, and, well, that's it essentially. So this is less confusing than the other equations. And finally, we have two additional equations, which are due to the potential. So the potential, the Poisson's equation, is a second order equation, and we split it into two first order equations. That means this is now these two equations denote Poisson's equation, and we get in the end we do now have a sixth order ordinary differential system containing as a parameter the eigenfrequency, and in addition to the eigenfrequency the harmonic degree L. So I don't want you to discuss this in detail. It's just as to give you an impression how the final result looks like. The zeta here is the Lagrangian displacement. P, T, well, I promised you some authors take a mixture of Lagrangian and Eulerian variables. Well, I did it myself. Zeta is the relative Lagrangian displacement, but P, T, and L are the relative Eulerian perturbations that are used here. In this, just to complete the notation here, LPH is the luminosity at the photosphere, and rho c is the central density of the star. Phi and psi are the perturbations of the gravitational potential. Well, and as I said before, these equations include a transformation of the variables according to Q going to Q over R to the power L for the numerical treatment of ambiguities in the center of the star. Okay, mainly motivated, these transformations are mainly motivated by a convenient numerical treatment. Of course, what is left? What do we need to discuss? The boundary conditions. Okay, so we need to care about the boundary conditions, and it's quite similar to the radial case. We have a singular point at the center, so we have regularity conditions at the center of the star, and the boundary conditions at the photosphere, at the surface of the star, are ambiguous because our model is not the physical boundary of our star. Okay, so without deriving them in detail, the boundary conditions may be read off from the equations. You write the equations in a form such that all coefficients are regular, do not diverge. Then you get, of course, some factors which make the highest derivatives vanish, like here. So you see x equal to 0. This is the center, is a singular point. Fortunately, it's a regular singular point. Otherwise, it would be pretty bad. We couldn't interpret the solutions. So this term, all the quantities are required to remain finite. That means the left-hand side vanishes for x equal to 0, and it does so for all of these equations. Then we obtain, well, so we might obtain six regularity conditions, and fortunately it turns out each two of them are identical. So they occur in pairs. For instance, from the first and second equation, we obtain two regularity conditions which turn out to be identical. And from the next two equations, we obtain regularity conditions which fortunately turn out to be identical. The right-hand side, the left-hand side and the right-hand side vanishes, and the two conditions which are obtained from that are identical. And the same is true for the potential equations. So we get, for regularity reasons, we have three regularity conditions at the center. One of them is for the potential, psi equal to phi is one condition. Then we have pressure is given by the Lagrangian displacement, and the luminosity perturbation can be expressed in terms of the temperature perturbations. These are the three regularity conditions which are found directly from the equations, which need to be adopted in order to avoid irregular solutions. Okay, now we turn to the outer boundary, to the surface or to the photosphere. I already mentioned, similar to the radial case, these conditions are ambiguous, and one of them is the same as for the radial perturbations. It consists of Stefan Boltzmann's law. This is the linearized version of the Stefan Boltzmann's law in the variables, in the dependent variables, which we have used in this case. Well, another boundary condition is obtained by the requirement that we want to have a force-free boundary. Previously, in the case of radial perturbation, it was that the Lagrangian pressure perturbation vanishes. In the same condition, Lagrangian, not Eulerian, Lagrangian pressure perturbation to vanish is in the new variables given by pressure is given by a linear combination of the Lagrangian displacement plus the perturbation of the potential. Why should we take Lagrangian pressure perturbation to 0 and not the Eulerian one? I think I commented on that this morning already. Well, you can perturb the surface of the star, and what you want is that at the co-moving surface, so to say, if you have a vacuum outside and your star inside with a finite pressure, then you would want that at the perturbed surface the pressure perturbation should be 0. And that means that the co-moving pressure perturbation should be taken to be 0 and not the pressure perturbation at one fixed point, because the surface of our star is allowed to move. Okay? So this is the Lagrangian pressure perturbation, which is set to 0. And for the potential, we have an additional condition, a boundary condition. This condition is derived from the assumption or from the requirement that outside our star we have a a vacuum solution for the gravitational potential. Outside our star, we assume there is vacuum. So the solution which you're looking for is Poisson's equation in the form delta Laplace operator acting on potential is 0 there. So we have a solution in the vacuum for the potential, and this solution of the vacuum solution should continuously be connected to the potential inside our star. And this condition of continuous connection of the potential to the vacuum solution gives you that psi is equal to minus 2L times the potential perturbation phi. Okay, that's for the boundary conditions. We do now have a sixth order boundary eigenvalue problem, very much like the one for the radial perturbation, with 3 boundary conditions at the center of the star and 3 boundary conditions at the surface of the star. Okay, what is different once we compare it to the radial problem, which is the case L equals to 0? Well, it is, compared to the radial problem, it's of 6th order rather than of 4th order. Else there is not a big difference between these two systems, both concerning the physics and both concerning the mathematics. So radial problem is 4th order, and the non-radial problem is of 6th order. So we need to solve a higher order problem, which caused in former times a big problem, because the higher the order of the differential system was, the more complicated and the more work had to be done numerically for this in this case. Of course, there is some physics which is entering now once we consider non-radial perturbations, for instance, which effect will be coming in, which is not present once we consider radial perturbations. What will? Okay, I think we are at the end. Okay. What is physically? What is there any new physical effect which we expect once we consider non-radial perturbations rather than radial ones? Can you think of? Yes, buoyancy will certainly now come in, because radial perturbations would prevent or would not allow for buoyancy effects. Now buoyancy effects are expected to play a role, but the input physics is not very much different from that what we did for the radial case. The same physics input was there, but the result of considering a non-radial or a non-spherical perturbation rather than a spherical one will be to allow for some additional physical effects, and we will study then in the following lectures in detail. Okay, now we saw we have either a 4th order or a 6th order problem, boundary eigenvalue problem, and we would like to solve it. Analytical solution is not possible, so we have to resort to a numerical solution. And the question is now how to solve this 4th order or 6th order differential problem, boundary eigenvalue problem. May I now have? Okay, thanks. So the mathematical structure of the linear perturbation equations and their solution. Okay, we have the mathematical problem consists of solving a system of ordinary differential equations for complex variables of 4th order in the radial case or 6th order in the non-radial case. Well, if we combine all the dependent variables in a vector y and denote the independent variable by x, we may write this equation or this system of equation in the following form. Y dash, this vector, is a big matrix times the vector of the dependent variables. This is a short way to describe or short way to write the differential equation in a matrix vector form. And Z is a 4 by 4 radial or by 6 by 6 non-radial matrix containing all the coefficients of the differential equations. It's a complex matrix because these coefficients are not all real, but there are also complex coefficients available in this matrix. The coefficients depend on the background stellar model. They depend on radius or mass, or on the independent variable x. So they depend on x, on the stellar model, and they depend on the two additional parameters, which is harmonic degree and the eigenfrequency sigma. Okay, now we have boundary conditions for these for this differential system of differential equations, and we would like to know how to solve this equation, this system of equations. That's already said. Z contains eigenfrequency and harmonic degree, and 2 or 3 boundary conditions are prescribed at any of the boundary, 2 for radial, 3 for non-radial. Okay, so what is done usually to solve this, to solve these problems? The first and the oldest methods are matrix methods. Matrix methods are work as follows. We split our integration intervals into n points. Points xi. Here I have taken out 3 points, xi minus 1, xi and xi plus 1, and our dependent variables are defined on these grid points. So we define a numerical grid, and we define the grid points, and we define the values of the quantities ui at these grid points. Ui means u at the grid point xi. Okay, well, the dependent variables are parameterized in this way, and the derivatives in the simplest case may then be given by value of u at point I plus 1 minus u at the point I divided by the difference of the grid points xi plus 1 minus xi. This is the simplest way to represent the derivative which occurs on the left-hand side of our equation, the y dash. That's the y dash here. The y dash contain derivatives, and these derivatives may be represented simply by differences with of the variables, the dependent variables, at two neighboring grid points. What we obtain by separating or by discretizing our system of equations is we get a huge algebraic system. So our matrix Z is now decomposed into even smaller parts. We have that the vector of each dependent variables contains now a vector of n values of the respective variables at the various grid points. So we, instead of the quantity u, which is the dependent variable, we have a vector of the length n, where n is the number of grid points, and u1 means it is the value of u at grid point 1. Un is the value at the grid point n. So all the dependent variables now correspond to vectors whose length is equal to the number of grid points. And these vectors are contained in the vector u here, and u consists of the vector containing the temperature, for instance, containing the vector of pressure and density and so on. So this vector contains all dependent variables. Its length is then 4. In the radial case, we have 4 equations. Since it's complex, times 2 times the number of grid points, and 6 times 2 times n in the case of non-radial case. So this matrix A still depends on the eigenfrequency, of course, and on the harmonic degree, and the dimension is the same as that of the vector u. So this becomes, if you have many grid points, if you want to have a high resolution, this becomes a very, very big matrix. And the eigenfrequency which we are looking for is determined by the equation, that the linear equation that the matrix A acting on the vector u should be 0. A necessary condition for this linear equation to hold is that the determinant of this matrix as a function of the frequency, eigenfrequency, should be 0. That means the 0 of the determinant of this big matrix, the zeros are the eigenfrequencies which we are looking for. Okay, this is one method to determine the eigenvalues. Well, this method faces some problem, because this determinant, the zeros of this determinant, need to be determined by iterative process. And for an iterative process, we need initial values, and these initial values have to be taken from some other approximation, and this approximation is not necessarily adapted to the problem. So you don't have, usually you don't have good estimates for the iteration of your eigenvalues. So the problem is the iterative solution of this requires estimates, and the second one is resolution. You never know how your perturbations look like as a function of radius. Once you start with the run or the behavior of your function u is not known a priori. A posteriori you can see it, but then you would have to have known the run of the eigenfunction to distribute your grid points in an optimum way. And if you go to higher order modes, which have many nodes, then the resolution you need increases drastically, and this might lead to the result that this determinant A becomes ill-conditioned, and you cannot determine its zeros anymore once the matrix A becomes too big. So this is a problem if the linear system becomes too big, if this equation becomes too big, too many members, then you face difficulties because the matrix A is ill-conditioned and you cannot solve this equation to sufficient accuracy anymore. So these are the matrix method, which suffer from resolution problems and from the problem that for the iteration we need to know the optimum distribution of grid points. Okay, an alternative to matrix methods are so-called shooting methods. Well, now what is a shooting method? Okay, we treat the system of equations as an initial value problem. So we start to integrate our 4 or 6 equations as an initial value problem from one boundary and try to reach the other boundary and to satisfy the remaining boundary conditions at the second boundary. Well, this has the advantage that we don't need to deal with resolution problems, because initial value problems do have a solution, and you can adjust during integration. You can adjust the time step, the integration step, according to the run of your solutions. So locally you can ask how fast do our dependent variables vary and how many points do we need to gain a sufficient resolution. This is a advantage of the shooting methods. So the resolution problems are gone, and we can start here with the two or three known boundary conditions, and we can try to iterate then our shooting until we match the two remaining boundary conditions. So we start off with two known boundary conditions and two boundary conditions we have to guess. Then we integrate to here and see, well, it's not yet satisfied. We iterate our initial boundary condition, do it once again, and iterate our two unknown initial boundary conditions until we match the boundary conditions here. Okay, well, so we have to iterate two or three boundary conditions, two or three initial conditions, which we do not know a priori, and we have to iterate them, so to say, a two-dimensional or even a three-dimensional parameter space. The advantage here, we do not need to have estimates for our determinant functions, and we do not have resolution problems. So this would be an ideal method to solve our linear stability problem. However, unfortunately, it's not that nice, because the iteration of the missing boundary conditions imply a numerical instability. I can, if you like, I have prepared some problems which show how this numerical instability comes about. What is the origin of that numerical instability? And it's usually called the so-called parasitic growth problem. So what happens? Somehow, by not knowing precisely the boundary conditions, by having to guess the remaining two or three boundary conditions, while we start the initial value problem, one catches divergent solutions. In the problems, there are in general, for systems of order higher than 2, actually the shooting methods work nicely for systems with order 2 and less. Of course, it's only at least order 2 to have two boundary conditions. For systems with differential order 2, the shooting method works nicely, but for systems higher than second order, we get this numerical problem. And our system are of fourth and sixth order, so we suffer from this problem. So what's going on is there are correct mathematical solutions of the problem which have diverging character. It's like, you may think of it in terms of having something like diverging solution from a regular singular point. In that case, you also have diverging solutions. Here you have diverging solutions for a different reason, but this diverging solution spoil the entire integration and makes and you can no longer use it to determine a determinant function or the solution. So these parasitic growth means the integration catches solutions which you don't want, but which explode exponentially and thus spoil your integration and the determination of the eigenvalue. Okay, so otherwise we would like to keep the advantages of a shooting method, no resolution problem, and otherwise no resolution problem, no principal problem of determining the eigenfrequency. We don't need any pre-estimates for the determination of the eigenfrequency, but we have to get rid of this parasitic growth problem. So the aim would be, we would like to have a numerically stable shooting method, and well, to reach a numerically stable method, we should not have an ambiguity in the initial condition, because the ambiguity in the initial condition leads to the capture of this diverging solution. So if we could avoid, or if it would possible to have unique initial conditions and to get it at the same time numerically stable, which might be the fact, because this capture of diverging solution is the reason for the parasitic growth problems, we might be able to use a shooting method to determine the solution of our boundary eigenvalue problem. Well, the answer is there is in fact a method to avoid ambiguous initial condition, which is at the same time numerically stable, which in its nature is a shooting method which does not suffer from resolution problems and from problems concerning the initial guesses for an iteration. And this is called the Riccati method, which I regret is not very much known among physicists who solve these problems, and also not among mathematicians. So I would like to present you here the use and the results of the so-called Riccati method. Well, what is done once we consider the Riccati method? We rewrite the pulsation equations in form of two vectors u and v and four matrices A, B, C, and D. So we consider the original system. The original system had the form y dash is equal to some matrix times y. And y contains the dependent variables, 4 for the radial case, 6 for the non-radial case, and this is either a 4x4 or 3x3 matrix. So we split this matrix Z into 4 matrices. So this is Z, and what we are doing, we split it into 4 parts. This is matrix A, B, C, D, and the vector Y, which was here, Y was the vector here, Y is split into 2 parts, U and V. So for the 4x4 system, for the radial case, A, B, C, D is are 2x2 matrices, and these U and V are 2 vectors, whereas for the non-radial case we have 3x3 matrices and 3 vectors U and V. Okay. So, and then we rewrite the system of perturbation equation in the form U dash is A times U plus B times V, and V dash is C times U plus D times V. Just defining it on the basis of the original problems. Okay? Let's do it for the radial problem. For the radial problem, we may take zeta and t as the u vector, the v vector as L and P, the 2 vectors, and the matrix A. Well, I have to convince you, I write down here the first 2 equations of the radial problem. We had zeta dash is C4 times 3 zeta plus alpha times P minus delta times T. This was the first equation. And the second one for T dash, so this would be the U dash, the derivative of the vector U, which is given by the first 2 components of our original equation. This is nabla naught times L over L rad times L minus 4 zeta plus kappa P times P minus 4 minus kappa T times T. Okay, so we can just read off from this equation what the matrix A is. A is the matrix which has to be which has to give the first two components with multiplication by u. So u is zeta. So this is 3c4. We just read it off from the equation. So the first component in the A matrix is 3c4. The second one is a coefficient of delta. This is minus delta times c4. And the second row here is the component, the coefficient of zeta of the second equation. This is minus 4 times nabla 0. And the coefficient, the fourth component or the fourth matrix element is the coefficient of t, which is minus 4 minus kappa t times nabla 0. It's very simple to define these matrices. You can simply read off from the original equations. Nothing behind. Okay. You can do it for the other matrices. You can do it yourself, how to define the matrices A, B, C, and D from the original equation. And similarly, of course, for the non-radial system. Now we define a Riccati matrix R, either 2 by 2 or 3 by 3, simply by defining U is some matrix R, a 2 by 2 or 3 by 3 matrix times V. Okay, now let's differentiate this relation and insert from the original equation U dash and V dash and the definition of the Riccati matrix R. So U dash, of course, U is R times V. U dash is R dash times V plus R times V dash. For U dash, we have the original equation. This is AU plus BV. Let's go back. U dash is AU plus BV, and V dash is correspondingly, V dash is CU plus DV. Just assuming the original equations. Now, U is given by R times V by definition. This is also here. U is R times V, and we end up with a matrix equation which acts only on the vector V. So, collecting all these terms, we are left with the following equation. R dash plus RCR plus RD minus AR minus B acting on the vector V is 0. Now we haven't specified the vector V. V is arbitrary, so we have that the matrix differential equation has to be, the matrix differential equation given by this bracket has to be 0 independent of the vector V. So we have a matrix differential equation which does not resort to the vectors U and V anymore. So we express it in the following way. Matrix differential equation means for each matrix element we have a differential equation. That means R dash is given by B plus AR minus RD minus RCR. We are left with a nonlinear matrix differential equation. So what did we achieve? So far, nothing. But, well, let's now have a look for the initial conditions for integration. Well, we can consider this now as an initial condition. If we have unique initial condition for our matrix, then we have a unique, or we have an unambiguous solution. We have always a solution and a well-defined solution for the matrix R. How do the initial condition look like? Consider, for instance, the inner boundary, that means the center of the star. We have our two 2 or 3. In the case, let's consider the radial case here. We have 2 regularity conditions there, namely 3 zeta plus alpha p minus delta t is 0, and the second one is that of adiabatic changes of state. 1 over nabla adiabatic minus p is 0. This is the second one. We can write it in terms, or we can solve it for zeta. So zeta is minus alpha over 3 plus delta over 3 nabla adiabatic. Let's start here. T is p times nabla adiabatic is one case. We can solve also for the Lagrangian displacement and replace the temperature variation, the temperature perturbation by nabla adiabatic times p. Then we are left with zeta is minus alpha over 3 plus delta over 3 times nabla adiabatic times p. Now go back to our vectors u and v. Okay, we rewrite it in matrix form. This was zeta t was our vector u, and the vector lp was our v vector. And both are connected through the matrix AR. So this would be the matrix if we take u and v at the center, the values at the center, then this would be the value of our R matrix, our Riccati matrix at the center. Now we write these boundary conditions in the matrix form, or we read off from these boundary conditions what the matrix form is. Well, these zeta and t, these are these two variables, depend only on the pressure perturbation. So the coefficient of L will be 0 in any case. And the coefficient of P for the first equation is minus alpha over 3 plus delta over 3 nabla adiabatic. And for the second equation, we have a nabla adiabatic here. So what did we receive then? Even if zeta, t, l, and p are not unique, are not unambiguous, there is some degree of freedom in the choice of the boundary conditions in terms of zeta, t, l, and p. Well, what about the Riccati matrix at the inner point, at the bottom point of our integration interval? Is there any degree of freedom in our Riccati matrix? Well, alpha, delta, nabla adiabatic are known from our background model, from the hydrostatic model. So all these coefficients are known, precisely known. There is no degree of freedom, there is no choice how to choose the Riccati matrix at R equal to 0. The same is true for the Riccati matrix at the outer boundary. You can do this procedure for the outer boundary condition and also define a unique, unambiguous Riccati matrix R. Okay? So what does it mean? Now we have achieved what we have wanted, because we wanted to get rid of the ambiguity in the initial conditions for the shooting method. Now we have unique, unambiguous initial condition, and we can start the integration without any ambiguity concerning the initial condition or the boundary conditions. That means we can take this equation and we start an initial value integration with this nonlinear Riccati equation with uniquely or unambiguously defined initial conditions. And this can be done either from the inner boundary or from the outer boundary. It's in any case, both at starting the integration either from the inner or outer boundary condition is equivalent. In any case, we do have unique, unambiguous initial conditions. So we got rid of the ambiguity in the boundary conditions, and I promise you at the same time we have gained numerical stability. So this is a numerically stable way to integrate these equations, and in an unambiguous way to integrate these equations. Well, and it can be done nicely for any size of the system. The size can be, for the Riccati matrix, can be 2 by 2 for the radial case, 3 by 3 for the non-radial case, and even for higher order systems, should they exist, this method can be applied. Okay? So how is the strategy then? If we start here, R is unambiguous. Well, you say, do I have to finish here? Probably. Well, we could have defined our matrix R also in the opposite way. So just saying not U is R times V, but who tells you that you could not just take V is some matrix times U? Well, this would then be, if the inverse of the matrix R would exist, it would be the inverse of the matrix. So you can equivalently define the Riccati equation and also the boundary conditions by assuming the inverse of the Riccati matrix, simply by inverting this relation. This is equivalent to this way to define Riccati matrix, and sometimes it's also needed. For instance, if you at the photosphere can only define on the basis of the boundary conditions only the inverse of the matrix. It may happen that it's not possible to define R, but it is possible to define the inverse of this matrix. In that case, either the Riccati matrix or its inverse is provided unambiguously at the boundary. So we have unambiguous initial conditions for R, and A, B, C, D contain the information of the equilibrium stellar model and the parameters L and sigma. So what I said already is, alternatively, we may define V is S times U, with S being the inverse of R, should R2 minus 1 exist. Well, this leads to a Riccati equation which looks very much similar, but where the matrices are simply exchanged. So this leads to a Riccati matrix with S, for S, where simply compared to the Riccati matrix with R, the matrices A have to be exchanged with D, and B has to be exchanged with C. So this is equivalent. Okay, so the last step would then be, how do we determine, we do now know how to integrate it, but how do we determine what is left, namely the determination of the eigenfrequency sigma? Okay, but I think I have to stop here, so I will tell you this next time. Thanks. Yeah, okay.
When we adopted this Riccati method, we
Yes.
went from a linearized system to a non-linear equations.
Yes.
So what exactly will happen when we are going from this linearized system? Will you capture some non-linear effects?
Hopefully not. No, we see that what I try to demonstrate is that the linear system is equivalent to a non-linear matrix system. This can be explicitly shown. I hope you agree with the derivation. But what do you mean by capturing non-linear features?
I may be confused by my statement that we are still in a linear system.
Yes,
So
we're starting from a linear system, and for numerical reasons, we switch to a non-linear equation. The non-linear system is numerically more stable than the linear one. The main reason being that we cannot, in the linear system, we cannot formulate the initial conditions for a shooting method in an unambiguous way. We always have to guess the remaining, the conditions which are not known at one boundary. So we only have 2 boundary conditions, and for an initial value integration we need 4 of them, so we have to guess 2 of them. And this causes the numerical difficulties. Why? Well, I can argue, or I can give some arguments why the linear system is unstable and why it gives, in a shooting method, why it gives problems with parasitic solutions. Unfortunately, I cannot give you a proof why the nonlinear system is stable and does not suffer from the parasitic growth problem. Maybe it has to do with the unique initial conditions, which cannot be formulated in the linear system, but which can be formulated for the nonlinear equation. But I'm not aware of a strict mathematical proof why the Riccati method should be stable. I have not come across. Probably it's pretty difficult to prove that solution of the Riccati method is numerically stable. Does that answer your question?
Yes.
Well, features of the linear system transfer to the nonlinear system. What I try to show is you can construct from the linear system, you can construct a nonlinear equation. And the nonlinear equation has the advantage that we can formulate the boundary condition in a unique way for an initial value integration. That's the main point. Whether there is a proof for the stability of the Riccati approach, I'm not aware of. But so far, it always worked. I have never come across a situation when the method has failed. Yeah.
I had a question.
Yes.
Like, when you are going from the shooting method to the Riccati method,
yes.
you are like trying to solve the issue of the divergence problems that arise due to higher order systems, right?
Yes.
So in the shooting method, you had a you still have to define a grid,
Yeah, you have a finite grid, of course, a
yes.
local finite. Locally, it's always a finite grid. You go from integration step to integration step. But in a shooting method, you have the advantage that you can adjust this step locally. If you see if you watch your dependent variables, if they vary a lot, then you take smaller steps. If they vary not as much, then you can take the steps bigger.
Yes. So when you go to the Riccati method, what happens to the grid? Do you still use a similar sort of grid, or do you make any do you change how you define the grids, or?
No, I don't change because it depends on the integrator. What you use, you can use any initial value integrator. It could be a Rourkela or what else. Important is, of course, you adjust your integration step locally to your local needs. So it decides either it's irrelevant whether it's a linear system or non-linear system. The code or the scheme, the numerical scheme, adjusts the time or the integration step simply by looking for the variation of the variables. If the variation of the variables is big, it takes a smaller step. If the variables do not vary much, then the step will become larger. So it's done irrespective of the equation, simply by considering the variation of your dependent variables. Is that sufficient? Okay. So for integration, you may take. There are many initial value integrators around, and you can take any of these, which usually they have a variable integration step included. But the integrator is not really important. You can take many of these. The question is which equation you are solving.
So just any adaptive
Yes,
grid.
any adaptive
Is
method.
fine.
Yes, it will be fine.